All right, welcome to the Explainer. Today we're digging into a paper that tackles a problem that seems like it should be simple, but is actually one of the trickiest puzzles in urban mobility. So let's just jump right in with the core question. Why is it so hard to predict a simple bike ride? I mean, you'd think we have this figured out by now, right? We're great at estimating car travel times with incredible accuracy. But bikes? Turns out they're a completely different beast. And really, it all boils down to three big headaches. For starters, we just don't have a lot of good, clean cycling data. Then you've got the human element. Every cyclist is different. Are they commuting, just cruising? Are they an athlete or a casual rider? And on top of all that, cyclists, well, let's just say they get creative. They use shortcuts, pedestrian paths, you name it. They don't always stick to the grid like cars do. So, to get around all this, a new paper introduces a really clever model called DG4B. Here's how we're going to break it down. We'll start with the challenge itself, then get into the core idea, this tale of two graphs. We'll look at the architecture, a really slick trick they used, check out the real-world results, and then wrap up with what it all means for our cities. All right, first up, the Urban Cycling Challenge. You know, as more and more cities encourage people to get on their bikes, getting this right becomes absolutely critical. And it's pretty clear why the old methods we perfected for cars just don't cut it. Think about it. A cyclist's travel time is, well, it's all over the place. It depends on their personal fitness, whether they're in a hurry to get to work, or if they decide to stop for a coffee. And they don't just stick to the roads, right? They'll use bike paths, sidewalks, parks. Their actual network is way more complex. That huge variability just completely breaks the traditional models we use for cars. So how do you even begin to model that chaos? Well, this is where the paper gets really interesting. The authors had a key insight. Instead of trying to force everything into one single perfect model, what if you looked at the problem from two different angles at the same time? What if you used two graphs? And this is the tale of two graphs. First, you have the static road graph. This is the city's blueprint, you know, all the roads, intersections, the permanent infrastructure. It's the same for everybody. But then you have the dynamic trip graph. This one's personal. It's the actual, specific, directed path that one cyclist took from point A to point B on one unique trip. And this image just makes it crystal clear. Over on the left, that's the whole shebang, the entire Berlin road network. That's our static graph. And on the right, that's one person's journey, a single dynamic trick traced across that map. The magic of the DG4B model is that it's designed to learn from both of these structures simultaneously. Okay, so we have these two graphs. How does the model actually use them to learn something useful? Let's get into the nitty-gritty of the architecture. Basically, the model runs two processes in parallel. Think of it like two assembly lines working at once. One line is focused on the big picture, the static city map. It learns a rich understanding and embedding of the entire road network. At the exact same time, the other line is totally focused on the individual trip, that dynamic graph. And then at the very end, it brings the insights from both of those lines together to make its final prediction. Now, for the GNN experts watching, you've probably been waiting for this. The processor here is, of course, a graph convolutional neural network, a GCNN. And this is so important because the GCNN is what lets the model understand spatial context. It allows information to flow between neighboring road segments, so the model learns that, say, a steep hill on one street is probably going to affect the speed on the next street over. It's all about capturing those crucial spatial relationships. All right, now we get to what is, in my opinion, the cleverest part of this whole paper. It's a really elegant solution to that very messy data problem we talked about. See, the model doesn't actually predict travel time at all. Take a look at this. This is what the real-world travel time data actually looks like. You can see it's super skewed. You have tons and tons of short trips, and then this long tail of a few really lengthy ones. Now, if you do machine learning, you know this kind of long-tail distribution is a nightmare. Trying to directly predict a single value, like the average time, is almost impossible, because those outliers will just pull your model all over the place. So the authors did something brilliant. They just sidestepped the problem. They changed the question. Instead of asking, how long will this trip take, it asks, how fast is the cyclist likely to be going on this specific bit of road? So for every single road segment, the model doesn't output one speed. It outputs a probability distribution across a range of speeds. Like there's a 70% chance they're going 15 kilometers per hour, a 20% chance they're going 20, and so on. It turns a messy regression problem into a much cleaner, more stable classification problem. It's a really smart move. Okay, so the theory is sound. You've got dual graphs, you're predicting speed instead of time. It all sounds great on paper, but the real question is, does it actually work? Let's look at the numbers from the Berlin Simrad dataset. And the results really speak for themselves. What you're looking at here is the mean absolute error, basically how wrong the prediction was on average in seconds. So lower is better. And as you can see, DG4B consistently beats the other strong baseline models, like LightGBM and a standard MLP. And check out that improvement on short trips. Those are notoriously the hardest ones to get right, and DG4B really nails it. This box plot shows us something else, too, and it's just as important. It's not just that the average error is lower. Look at how tight that box is for DG4B there on the right. That means the predictions are way more consistent. There's much less variance. So it's not just more accurate, it's more reliably accurate. You can trust its predictions more often. So let's pull back from the numbers and the architecture for a second. This is a cool achievement for machine learning, for sure. But what's the real-world impact? Why does this actually matter for our cities? Well, the applications are huge. For city planners, this is a gold mine. You can finally identify where the real cycling bottlenecks are and make smart, evidence-based decisions about where to invest in new bike lanes. This could power the next generation of route planning apps on your phone. It helps figure out the absolute best spots for bike share docks. It's really about giving cities the tools they need to build infrastructure that actually works for cyclists. Ultimately, what this research does is give us a much, much clearer picture of how people actually move through a city on a bike. It brings us that much closer to not just promoting cycling, but being able to actively engineer cities that are safer, more efficient, and frankly, more enjoyable for everyone on two wheels. It really makes you wonder, what's next?